Hello guys, this is Chem 2125 Practical Organic Chemistry course, and this is a lab lecture for that course. And in this lab lecture we'll be looking at synthesis of benzoin. So specifically the benzoin condensation is where we refer to synthesis of benzene from to aldehydes. So remember that in the past 4 experiments before the previous experiment, we were carrying on the long base to the synthesis of hexaphenylbenzene. And if you remember, in those experiments, we finished the first pass. We synthesized stilbene from benzaldehyde and using the Wheating reagent, and then we make an addition reaction on stilbene to synthesize 2-bromostilbene, and then we conduct an elimination reaction on 2-bromostilbene to synthesize diphenylacetylene. With that, we finish the first pass, and the second pass to lead us to the second major reagent for the synthesis of hexaphenylbenzene is the one that we will be starting today. And the first mechanism in the second pass is to synthesize benzoin from benzaldehyde, and that is what this lab lecture will focus. So like I said, today's experiment will be on synthesis of benzoin from benzaldehyde, and we will look in the following slides. I'll show you the mechanism how we will be able to synthesize the benzoin. So we'll be using benzaldehyde, and our destination is to synthesize the benzoin. It's a 2 6-member ring compound having both the carbonyl carbon and the hydroxyl group in it, and you'll see how we will synthesize it in detail. So in benzene condensation, as in many condensation reactions, the action of a base is very crucial. And normally for benzene condensation, strong bases like cyanide is used as a base, but because it's highly toxic to use in the lab, we will use thiamine as an alternative base catalyst for the reaction. The catalyst purpose is just to abstract a proton, and that will facilitate the reaction by creating a negative charge in the substrate. So what happens is, when thiamine reacts with sodium hydroxide or with the base, because in the experimental part you'll see we'll be adding also a base into the reagents, and the base abstracts a proton from thiamine, and that will because the thiamine we use is a thiamine hydrochloride, and that base will create a zwitter ion, because this is thiamine is a nitrogenous base, and it has a plus sign from before. Now when the base abstracts a hydrogen, it creates a zwitter ion catalyst. Zwitter ion is just an ion with both hydrophobic and hydrophilic characteristics, and that's chemically what you see in this slide. This is how it's described. The zwitter ion is most common sinus in amino acids, as it it's a characteristics of the amino acids, because in amino acids you have the carboxylic group and the amine group, and when both the carboxylic acid and the amine group hydrogens are abstracted, the resultant product will be a deuter ion. So for thiamine halide in general, where X can be chlorine, bromine, are used, and for this experiment we'll be looking to thiamine hydrogen chloride specifically. That will be our catalyst source. So the above mechanism is how the deuter ion is produced, and just we will have a couple of a bit lengthy mechanism in the following slides. So here we need to just symbolize some of the structures for the ease of representation during the mechanisms, and the fragment at the bottom we're going to call it R2, the hydroxyl attachment of the thiamine we're going to call it R1, and we'll use those symbols as of this slide. So what happens, the created negative charge will attack one of the benzaldehyde, 1 mole of the benzaldehyde. Specifically, it attacks the electrophilic carbon. Then this is a nucleophilic addition to the carbonyl carbon, and the negative charge will attack the carbonyl carbon. Carbonyl carbon oxygen opens and then takes a proton from water because water is also a reagent in the reaction, and takes hydrogen from water and becomes this intermediate. Okay, and we then use this intermediate to react with a base, and the base again abstracts the aldehyde hydrogen in this case, and the aldehyde hydrogen will leave its electrons to the carbon, and we then have a charged separated to an ion pair compound separated by charges. Notice that the charges are not adjacent to each other; they are just in a two different carbon atoms that are at two single bonds from one another. So what happens is, because this charged particle, we cannot call in this case we cannot call that this is a deuter ion, as the charges are not adjacent to each other. But what happens is this minus sign delocalizes to the nearest carbon atom, to the carbon atom part of the thiamine, and then it will make the double bond. Then this fragment is the important intermediate that will react with the second benzaldehyde that we'll be using. In fact, these are just resonance contributors. You can use a double bond, or you can use the charge separated compound before it undergoes resonance. But this is to show you that the compound is stabilized by resonance, and the most stable resonance form of the compound is where the negative charge makes the double bond. So then in part 3 of the mechanism, this minus sign again attacks the carbonyl-carbon openness, and in this case it takes the hydroxyl group from intermolecular action by intramolecular action from the neighboring hydroxyl group. And what happens is the oxygen hydrogen pi bond will delocalize down to make the carbonyl-carbon, and that will displace the thiamine fragment, which will be the catalyst in this case, and then we have the catalyst recovered and the final product benzoin formed. So in the experiment we'll be using the clean and dry Erlenmeyer flask, and to that we'll add 1.04 gram of thiamine, the catalyst, and 3 milliliters of water, followed by 8 milliliters of 90% ethanol. Looks like it's an analytical grade, and then we add 3 milliliters of aqueous 10% sodium hydroxide, followed by 3 milliliters of benzaldehyde, our major substrate, and we mix them thoroughly. In fact, it's recommended that we agitate the mixtures after each addition, and then we keep the mixture to react overnight. So certainly we're not going to get the product immediately as in the other experiments. For this one we're going to let it react for overnight, and we can get our product in the next day. The product should be isolated, and to do that we will be using a funnel. The textbook recommends us to use Hirsch funnel because the Hirsch funnel is like Buchner funnel, but with the shape of normal separatory. With the normal funnel that we use, they are the same. I mean, physically speaking, they are the same. With respect to the purpose, they are the same. But as you can see, the Hirsch funnel is kind of narrow, and that facilitates the gravity filtration. But because we do not have the Hirsch funnel in the laboratory, we will be using the Buchner funnel. And so one of the problems in synthesizing crystals is that crystals might not be formed, and this is also an issue in recrystallization experiments, if you remember from your organic chemistry 1. And the solution to facilitate crystal formation is either to cool your product in ionized bath, which is the first preferred way, or if that does not work, we can scratch the walls, the inside walls of the flask, in this case the Erlenmeyer flask, with a glass rod, or if you have a stirrer or a spatula will work. If not, the third option is to use a small crystals, pure crystals that are already formed as a initiator for the growth of the crystals. We call them seed crystals because they initiate the formation of the crystals. If we have a pure benzoin in the lab, that's preferred way to use. Otherwise, we will be using the benzoin from other groups who already synthesized the benzoin. In washing benzoin, we have to stick to use 50% of ethanol and cold water. Most importantly, the 50% ethanol is necessary to stick to here because benzoin is soluble in ethanol, but it's insoluble in water. So that's the important procedure that we have to stick to here. And then we dry our compound and weigh the actual yield. So we are on the mechanism to synthesize hexaphenylbenzene. As I explained in the beginning, because throughout all the previous 4 experiments, we have been doing the first pass to synthesize the hexaphenylbenzene, and then we're starting the second pass here. And this benzoin will be used for the synthesis of the destination compound, but we don't need to further purify this one in the further synthesis of the hexaphenylbenzene. So as usual, because we're working with organic compounds, we'll be doing spectroscopic experiment to know what is what, or to be sure that we have synthesized the compounds we are trying to synthesize, and we'll be using IR and NMR as usual. Safety matters regarding this experiment. If you remember from the experimental procedure, we used sodium hydroxide. Sodium hydroxide is a strong base which is corrosive to our tissues. For that, we have to be careful in using it. And then purification of benzaldehyde. I think this is something related to the second experiment during this course. If you remember, the first one was safety, second one was purification of benzaldehyde. If you're interested, you can go back and visit that experiment. But we need benzaldehyde as pure as possible, because it may affect our yield in the end. If the benzaldehyde we use here is contaminated, and then we will have very small yield in the end. So how benzaldehyde is purified, it's all described in the second experiment in this course. It's not a complex kind of experiment. We just wash the benzaldehyde first with sodium bicarbonate. You just wash it in a separate phenol with frequent shaking, and then you wash it with water, and then after you can dry the product using magnesium sulfate, and that's how we wash the benzaldehyde. That's all for this course, for this lab lecture, for this week's lab lecture. If you have any question or comment, I hope I will see them in the YouTube comment section, and thank you.